Today we start the generalized model as compared with the finite state machine. We are going to discuss push-down automata. Push-down automata or generalized model as compared with the finite state machine. We have seen in case of finite state machine, there are much restrictions on that. We cannot remember sufficiently large information. The only way to remember the information in FA by means of transiting the state. In case of FA, we are not going to provide any kind of auxiliary storage. So we have very extremely small amount of memory in finite automaton, and using only the small amount of memory, you have seen that we can do a lot of jobs. Now we will see the generalization of the finite automaton, which is called push-down automata. So push-down automata are more powerful as compared with the finite state machine, means FA. Let us see one informal example for the push-down automaton. Assuming that we have some factory, okay, so you may have some factory. Factory means those who are producing some kind of goods, like say, and the factory is going to produce the cups and plate. So in the factory we have the two unit. You can say let A, unit A is responsible for producing the say for example plate, okay, and you have the unit in the factory B which is going to produce the cup. So only these two items are going to manufactured in the some basic company, some factories, you can say. What actually we want to show here is, see, if you have two unit, one is say you have the unit A, this is assuming that this is the unit A which is going to produce the plate. So we have the unit A. You have also the unit B, okay, and unit B is going to produce the cup. This is okay. So plate generally we mean like this. We use in the taking the tea also, and the cup means you might have seen the cup like this. In your life you might have seen cup like this. So this is cup and this is the plate we are talking about. So you have two unit, one is producing cup and other is producing the A is for the plate and B is for the cup. What we mean that you have some conveyor belt, here you have the belt, and here actually this is the point of receiving. So here this is the point where someone is going to receive the items, okay. So here you are going to receive, from here also, okay, and this goes to, and you are going to receive here. Here is some form of the person, or you can say that we have some robot, okay, we have some robot which has only the two hand, and it can't remember any much information, means it can't hold the items more than two, because it has only the two hands. In one hand it can, if it is going to hold cup, then in other hand if it is free, then it can hold only the plate. No further item this robot can hold. So we have the unit A which is going to produce the plate, right? So plate is coming like this. This is the plate, and it is coming through this belt, and here unit B is going to for the cup, and this cup is coming through this belt like this, okay. So once the cup is received at this point, then robot is going to pick up the plate. If it is going to receive the plate, then it is going to pick up the plate in one hand. Once it is going to receive the cup, then it is going to assemble like this. So it is going to assemble like this, and okay, then its job is done, and now this is transferred to somewhere else. Then again both hand is free, again some cup and plates comes. Maybe it may be happen that first cup is coming, then next robot is waiting for the plate, or plate is coming first, then robot is waiting for the cup. So cup and plates are coming in synchronized manner. We assume that the synchronized manner means if one cup is coming, after that your plate is coming. So there is a synchronization in the both the unit. So the work is going on. There is no problem. We don't have any problem here. This is going on. And see, you can simulate this thing as your DFA, where you have very small amount of memory. Robot has very small amount of memory to hold. Means it has only the two hands where it can hold the any one of these two items. Nothing else. It can hold maximum 2 items. So this is the way we can think that okay, it has very small amount of memory, but even if this kind of synchronization is there, then your work is going on, there is no issue. But what happens sometimes, if the unit A goes down, then you are not producing the plate and only cups are going there. Then if it can hold maximum 2 cups, nothing else. So what happened, this unit also forced to stop producing the cup, because we need to assemble the cups and plate and we have to transfer. So unit B has to wait for the unit A to work again, or it may be possible that unit B is not working and A is working, then also A has to wait for the B to work. So this is the problem. So this kind of, if you have this kind of setup, we have extremely amount of very little amount of storage, and we can do only this kind of job. But somebody say that okay, if say unit A is working and if B is not working, then why should I wait for the B? I can produce the plates and I can store somewhere else. Once B is ready for producing the cup, then someone can take the robots to take the cups and access the storage where plates it has stored, and then it can assemble. So for that, actually people think that instead of robot is having this kind of storage, we can provide the robot a storage of like this. We can provide a container near the robot, so that if this is the situation, this is the form of the storage we have given to the robot. So if you are given the storage like this, which we say that this is the auxiliary storage we are providing for the robot. So you have the auxiliary storage. Okay, so we have the auxiliary storage. So what happens if only plates are coming, then your robot is going to store the plates, and if cup is not going to produce, then robot is going to store the plates only. It sees that the robot sees that once item is coming, actually robot is also unaware of whether which item is coming next. So robot has to say that okay, if only plates are coming, if plate is, robot is going to receive the plate only, and it sees that okay, what we assume here that this is the form of the stack, means robot has to access only top point, and it cannot pick up the plates from the bottom, so it can only access the top plates. So if robot is going to see that okay, there is a plate is coming, and it sees that what is the top item in the container auxiliary storage, it sees that okay, yes, plates are there. If it is plate, then robot has to place the plate over the plate again. So this is the way, assuming that we have sufficiently large storage, so that your robot is going to store the plates like this. And sometimes once this it is okay, it starts working, then cups are also coming back, coming again. Then robot says that okay, here is cups are coming, says that okay, cup is there. And then robot has to see that what is top in this story, and sees that okay, top of this is plate. So robot says that okay, yes, I can pull pop from the stack. So it has to pop from the delete, means it has to take one plate from this stack, means it is the operation pop, you can say, and then again assembles the cups and plate. So you have this situation like this. So in this way, once it is going to receive cups, then one by one, and sees the top is plate, then it is going to delete and assembles. Again it receives the cup, says that okay, yes, top is plate, again assembles, and again sees that okay, this is cup, and but here at the stack we have the plate. So it deletes, means it assembles like this. So you have taken the cups, and if it happens that okay, plates are not coming, only cups are coming, then also robot has to store the cup here. So your robot is going to store the cup. Okay, again it says that okay, cup, only cup is coming, and says that okay, top of the storage is cup, then it is going, robot is going to store the cup again this way, like this. Again says that okay, only cup is coming at this point, so it again it restores. So when robot sees that okay, no, here I am going to receive the plate, then it sees that what is top of the stack, this is the top of the stack. So top of the stack is cup, and here is you have the it sees that okay, there is a plate, so it need to pop from the stack the cup, and it has actually to it is going to assemble like this. Again it says that the plate is there, then it has to delete from the top and assembles like this. Again it has to delete from the top and assembles like this. So there is no issue now in this case whether the unit A is working or it is not working. If any one of the unit is working, then also robot is not ideal. The robot is going to store at the container, but only robot says that what is top at the stack. So see, actually you can think of this as the state transition. So robot has inputs are like cups and plates and cups you have. So once cups and plates are the input for the robot, and robot in some form, some state, you can say, once it receives the item, say plate, and receive, it has some state, robot has some state, and then it has to access the top of the memory, stack top, and if it found that okay, stack top is cup, then it is going to delete from the top, deletes from the top, and it assembles like this, like this. When it is going to receive the cup, input is cup and top of the stack is cup, then the cup is going to push. So robot is supposed to push cup onto the stack. If top is cup, here is also cup, then robot is supposed to store onto the stack, means it is going to push into stack. So see, now you have the three situations here as compared with the finite automaton. You have your finite automaton transit on behalf of the current input, what is it is going to receive, and the current state. So on behalf of the state and the input it is going to receive, your app is going to make the transition. Now in case of the PDA, pushdown automaton makes the decision on behalf of the three information. One is what is the current state of it, and what is the input, and what is the stack content. So on behalf of these three information, it decides that whether it should transit the state, or whether it should not transit the state, or whether it should modify the stack, or whether the stacks should not be changed. So here we have the additional thing that is the which is important, and that one is the auxiliary storage. So we are going to provide the auxiliary storage here And now this, since this is the memory we have provided, like the stack, this is the stack memory, and hence that's why this is actually called the push down automaton. You can push the information, you can down means you can delete the information from the top. So in case of the PDA, we are going to provide push down we are going to provide stack as the auxiliary storage. So once you provide auxiliary storage to the FA in the form of the stack, this will become now push down automaton. And now this machine will become more powerful as compared with your FA, finite automaton. So this is the only difference as compared with the FA, that is, we have now memory for remembering the large amount of information. So you can remember the long length of the strings also. If you want to remember, like in case of the FA, if you want to remember the string 2, 3, 4, you see that how you have to transit the state, because the only way to remember the information is by state transition. Here you don't require to transit the state, you can push onto the stack and you can remember what information you have stored on the stack. So now this machine will become more powerful as compared with your finite automaton, only by providing the auxiliary storage. So, and this auxiliary storage have restriction. You can access only at the top of the memory. You can't access at the bottom. And see, when there is no item is coming here, if you don't have any item, means if there is no plate or there is no cup, no information is coming, means you are not going to receive any information, any cups or plates. Then robot says that okay, the input exhaust, means unit A and unit B are not going to produce any item, and hence your robot is going to the transit to some state which we can say that it is going for the final state, or it is going for the ideal state. It comes to know that okay, there is no further input. Now it has to make the decision that okay, I have done the jobs for the 2 days work. So this is the way your machine is going to work. So this is somewhat informal definition, informal description of your push down automaton. So there are three important information here. One is the state. The main important thing is you have the state. Okay. So, and second one is input. And third important thing is stack contents. Stack contents. So you have the okay. So you have the stack contents. So you, on behalf of the three information, earlier you have made the decision on behalf of the state and input. Now your machine is going to make the decisions on behalf of the three information. One is the state, other one is the input it is going to receive, and third one is the, it says that what is the current top, what is the top of the stack, what is the current item stored at the top of the stack. So on behalf of this, your machine is going to make the decisions. And see, this just like in this case, once you are nothing is coming, means you don't, nothing there, no plates, no cups, then it is not going to receive any input. Then it says that okay, if there is no contents in the top, then it can signal that okay, the successful completion of the job, means every whatever stored in the memory, means whatever items it is going to, it has stored on the into the memory, and the same items it has the assembled. So it has finished the job. When there is no input, no contents in the auxiliary storage, then it can say that okay, yes, it goes to the final state by saying that yes, I have done the job, there is nothing pending. So here also your input may exhaust. Once your input exhausts, then you may need to make the decisions on behalf of the contents of your stack. What is the contents of the stack? If some item is there, and your input exhaust, then you can say that, okay, there are some item remaining and the work is pending. Your robot may not go to the final state. So here once input exhaust, then also you have to make the decision on behalf of the stack contents. This is one thing. Sometimes so your stack can also be empty. So it has to see that your stack is empty. Okay. So now this is the way you can say your PDA works, push-down automata work. Now we are going to see the formal definition of your PDA, push-down automata. So we are talking about the machines, which is the PDAs. We can say PDA is the push-down automaton, and we are talking about the PDAs. A automaton PDA is a 7 tuple, and you can remember that your FA was 5 tuples. You have only 5 information in FA. Now your PDA is 7 tuple. What extra things you have in PDA? You have the stack. Okay, so Q again. Q is what? Q is the finite set of states. Okay, and sigma is input alphabet, and you have the tau. Tau is actually stack alphabet. Stack alphabet means whatever you are going to store onto the stack, let me say that, okay, this is the stack alphabet. So you have the stack, and you may have the sigma, like this, and sigma may contain, say, A and B. Sometimes you may require that, okay, you want to store these input also onto the stack, and beside these two symbols A and B, you may also require to put some more symbols onto the stack. So you have the stack, which we denote by writing the tau. This is the stack's alphabet, and this stack alphabet, there is no hard and fast rules. Every symbol of the stack alphabet can be different. Like we have the Z0. Z0 is the initial symbol at the stack alphabet. So we assume that at the bottom, the only symbol stored at the bottom of your stack is Z0. And what we assume that this Z0 is the initial stack symbol, and we never delete this symbol. We are not going to delete the Z0, and means you have currently your stack top is Z0. So once you see the stack top, it is Z0, and we assume that we don't delete this Z0, means we never pop the Z0 from the stack. So you have the tau, which is the stack symbol. This stack alphabet can be totally different as compared with the input alphabet, or it can also include the alphabet like this and some more symbol like capital A, capital B, whatever you have. But condition is only this must be finite set. Must have the finite number of elements. So if you think that you can work on these input, you can work. You don't require to take store other symbols onto the stack, or you can take some different symbols. And question is that whatever symbol you are going to store onto the stack, such are the stack symbols. And this set, the set of stack alphabet, this contains what are the symbols you are going to store onto the stack. Q0 is the initial state. Your machine starts from the Q0. Z0, initial stack symbol. It is the initial stack symbol. And you have the A. A is what? A again. A is the subset of Q, which is set of final states, accepting state. So you can say that set of accepting state. And delta is the transition function. So you have seen that now PDA or push down automaton, formally you can say PDA is 7 tuple, M, which we can denote the PDA by writing the symbol M again, machine which contains the q sigma tau q0 z0 a delta. Q is again finite set of states. You are aware of this in the FA. This is the input alphabet. Sigma is the input alphabet. Tau is the stack alphabet. Whatever you are going to store onto the stack, these are the symbols. This tau contains all such symbols which you are going to store onto the stack. Q0 is the initial state from where your PDA start. Z0 is the initial contents of your stack, means this is the initial stack symbol. And we assume that this Z0 we are not going to delete. Always Z0 is there at the bottom. So you have to work after the Z0. A is the final state. Like in your FA, you have the final states. You may have only one final state or you can have more final state. Delta is the transition function. And here actually delta is very important. So we define delta like you have the state Q. You know that your machine is going to make the decision on behalf of three information. One is state, what is the current state of your machine. Other one is what is the input symbol. And also it can have the null also. When your input exhaust and then it is there is no elements from this sigma it is going to receive, means input exhaust, then on behalf of the null it is going to make the transition by observing the contents of this type. So you have the sigma union null, and now you have the stack alphabet. On behalf of the stack alphabet, means you know that this is the form of the stack, means your machine can see only the top of the stack. So this actually your machine is going to make the decisions on behalf of the current state and on behalf of the input you are going to receive, or it may transit on behalf of the null, and it sees what is the top contents of your stack. So any one symbol from the tau. So here you will see that what is the top in the stack, and on behalf of that your machine is going to make the decision. Where your machine can go? So your machine goes to any one of the states from the queue. It goes to any queue. Now once it goes to queue, you have seen that you are going to modify the stack top. You may delete the if you have stored some item earlier onto the stack, then on behalf of the input and current state you may need to delete some item, or you may need to push some more item onto the stack, means you are modifying the contents of the top. So one is you are going to modify the state, means you may change the state, you may transit the state, or you may remain in the same state, and also you are modifying the contents of the stack. Whatever current contents of your stack you are going to change. So your top symbols, on behalf of the top symbol, you may modify the top of the stack. So here you have you can store any string. Say you may have some A in the top of the stack. Okay. So once you see that the A is in the top of the stack, then you can replace this A with some string alpha which is taken from the tau star. So any strings alpha can be stored. You can replace this with this top symbol, or you may wish to delete this top. It means that you are going to replace this top item with null string. So null is also in the tau star. So once somebody says that okay, you want to delete, means whatever symbol you have here, you are replacing this symbol. You are replacing this symbol with null. Means we don't show null here. You are pushing down. This is the case. So here, what are the possibilities? You can have any possible strings. Alpha can be anything, you can say. So that's why you have the tau star here. So output of this move is, this transition function is, you have some state, or you have any strings from the tau star, where tau is the stack alphabet. So you see that this is the option is infinite actually. if you observe this side, so this is what? This is the infinite state. Why it is so? Because you have the string in the tau, you can form the string tau star contains the infinite possible strings. This means you have infinite possibilities. So like one possibility you can say, if you observe the stack like q cross tau star, and this represents the set, means you may have corresponds to this set contains you some state from the q, then you may have some string alpha 1, or some state from the q say q2, and you have the some string say like beta, or you have q1 and some string like beta. So you have this kind of information here. So one is from the state and other is from the string from the that can be formed by tau star. Alpha contains alpha, beta. These are the strings from the tau star. So we are you have the infinite possible set. So among this infinite possible, what we need? We need to consider some finite subsets of this. So say your output can be this only alpha 1, q1, alpha 1, q2 and beta. So this may be there, or your output, sometimes your output can be only this subset q1 alpha on behalf of the input and in q state, input and top symbol. Sometimes you have the three elements. So actually, and this set contains the infinite possibility. So what we assume that this contains the finite subsets. Finite, we are interested in finite subsets of this. So we are interested with finite subsets of this. Your output is, so you have some output is what? You have some output. So we are interested with some finite subset, means you can have only q1 alpha 1, or you can have only two output, one is this and one other is this. So you can have only output only one element, one pair, or you can have the two, or you can have the three. Just like in case of the finite automaton, it is the case of the, so you can observe here that by definition your push-down automaton is non-deterministic. This is non-deterministic actually. Why it is so? Because once you have included the null, whenever you have included the null, then machine is going to become the non-deterministic, because machine has to make the guess whether I should transit. It has now option that whether it should consume the input or whether it should not consume the input. But what we assume that here you should take the null transition at the end. Once your input exhausts, then you should take the null transition. This is our actually intuition to write null here. So we have some finite subset of this. So output can be any finite subset of this. So you have the bigger set and you can have some subset which has the finite number of elements. So this is just like one element, this is two element. Your output can have two elements, or you can have the subset which contains only one element, means it is going to make only one decisions. If it is output to q1 alpha 1 and q2 alpha 2, this means your machine can remain from some state, your machine can go to and modifying the top by alpha, or your machine, there is also option that your machine for the same input from the same current state, it can go to the state q2 by modifying the top, and top is replaced with the string beta. So this when the output is always 1, when the subset cardinality of this, whenever it is going to output and the cardinality is only 1, then we will say that yes, this is the case of deterministic one also, means every time your machine is going to make the unique decisions. So here this is very important thing. So you have, this is the transition function here. Okay, so Transition function is very important here. In case of the PDA, your PDA has transition function like this. In case of your FA, we have very simple transition function. Q cross sigma, and you are going for the sum Q. This is in case of the FA, we have seen. But here we have the three information, and we have Q, sigma union null, and you have the stack sim top contents, and then your machine can go to some subsets of Q cross tau star. Okay, so this is the formal definition of your push-down automata. Let us take one example. You can consider the language like it contains the string xc xr, where x is what? So x can be any strings from the AB clean star, you can say. So you have the some language as xc xr, where x belongs to AB clean star, means x can be null also, you can say, and or any combination of the any strings that can be obtained using these symbols A and B. So here you notice that here C is also there. Every sentence of this language contains this kind of string. Means C in the alphabet of this language, you have the C also. So this alphabet contains A, B, and C. You have the three input A, B, C, and C always comes at the only midpoint. And here this X contains only the strings of this is the A and B, and XOR means if you have X, if X is equal to say A double B, then XOR is equal to reverse of X. This means double B A. You are reading from right to left, reverse of X, so B B A. So what you see in this case, this is the language of palindrome you have already seen. So what are the strings in this language you have? You can have only C when X is null, or you can have A, CA, or you can have ABC and BA. This is X and this is the reverse of X, like this. So you have the string of like this. So this is the language of what? This is the language of palindrome, but this is the simplest language of palindrome, where you have the marker at the midpoint, and every string of this language has the odd number, length is odd number. So it can have at the midpoint you have only the C. This is one of the very simple example of your palindrome language, where you have marker at the midpoint, and once you come to know that okay, this is the C, it means you are going to receive the next part of your strings, which is the reverse of the previous one. So this is the marker. And if you write the grammar for this language, how can you write the grammar for this language? What is the grammar for this language? So whenever you write the grammar for this language, then you can say this is S derives A as A. The first symbol should be same as the last symbol, or you can have S derives, S is the start symbol, B as B, right? So either you can have A, then you must have the last symbol is also A. If you have the B, then last symbol you are going to ensure the C, and S can be terminated with symbol C. So you may have, since S is the start symbol, the smallest string is C, and you can terminate by writing the C here. So at the midpoint you will have the C. So this is the grammar for this language. And see, this is the grammar. What kind of grammar is this? This is the CFG. So you have every rules of this grammar is of this form. A derives alpha, where alpha is the string of terminals or non-terminals both. Alpha belongs to what? A string of terminals or non-terminals or terminals both, like this. So this is the CFG, means this is the context free language, you know that this is the context free. And if you want to construct the FA for this language, then it is very difficult because x can be of any length, and you need to remember that what x you have read, and the next part once the C comes, then you need to match uh, the first part you have already received. And in FA, you know that you can't do like this. So once you are reading from left to right, and you are not coming back. Okay, so you cannot verify. So in the case of the finite, if you try to construct the FA for this language, it is not possible because this is the context free language, and the FA is for the regular language. Context free languages are more expressive as compared with the regular language. So how can you construct the machine for this case? So it is very simple. If you want to construct the PDA for this case, so you can obtain the PDA. PDA is very simple for this case. So see how you can obtain the PDA for this machine. Assuming that your PDA starts from the state, say it starts from the Q0, you have the Q0, which is the initial state. Okay, so we have the initial state here, and what we need to see, you have at the initial state Q0, actually you need to read the first part of the string, say x. You are going to read the first part of the string x, and once C comes, then you need to change the state because you have to match now. So what you need to do in Q0, so if you are at the Q0, then what you have, so if you are at the Q0, this is the current state, and input is what? Input can be A, and at the beginning, you know that the bottom of the stack contains you have the bottom, and at the bottom of the stack, we have the Z0 as the initial symbols. Okay, so you can assume that like this. You have the stack, and at the bottom we have this Z0. So this is the initial stack content. Now your input can be A or B. You have the input either A or B. Okay, then at the midpoint you will see the C. So once the input is A and if top is Z0, you have input is A and top is Z0. So what you need? You need to store A because input is A. You are in the state Q0. Input is A, and top is Z0. So you have to replace this top with, you can say, A Z0. So input is A and top is Z0. So what you need? You need to push. In this way, you are going to push onto the stack. And whenever you have the AZ0, this is what? This is some strings which is taken from the tau star. Now this is the string which you have replaced with which we have replaced with the top. So assuming that Z0 was in the top, and you need to post, means you are replacing top with this string. And remember that this leftmost is corresponds to the top of the stack. So the next most symbol of this string is corresponds to the top of the stack. This means A will be in the top, and this will be in the next top to top. So that's why here you have the A, and now the top symbols becomes A. This is one situation. Other one is what? You have the input, you can have the input B, and your stack can, at the beginning, instead of receiving A, you are receiving the B. Okay. Once you are receiving the B, then you see that your job is only to store the information onto the stack. So you will have the VZ0. So B will be in the top. This is the leftmost. So you are replacing this Z0 with the strings BZ0. means B will be in the top and Z0 will be at the bottom. So here your output is what? Output is state. You are in the same state, Q0, and this is the alpha you have modified. This is the string from the tau star you have modified. So this is one situation. What are the other things? You can have so you can draw some more systematic so that you can. So this is for this and this is for this, and you can have further input. Now you have the A, and it may be possible that input is A and top can also be A. Like you have the A here already. Earlier you might have pushed the A and input is A. So what you need? You have to further restore this. So you can say this is A. Similarly, you can have input can be A and top can be B. So you need to push this input onto the stack. So you will have the AB. So input is A and top is B. So you are going to replace this B with AB, means A will be now top. You have pushed A and B will be next top to top. Similarly, in case of the B also, your input is B and stack can contains A at the top. So what you need to do? This is in the first part, so you are going to save. So you are replacing this top with the strings say BA, right? So you are going to replace the strings with the strings BA, and now B will be in the top and this will be in the next top. So means like if your input is B and top is A, your top is A, input is B, so you are going to push B onto the stack, means you are replacing A with BA strings. So B will be in the top, A is in the next top to top. Now you may have this situation, what input is B and top can also be B. So again, no problem, you are going to save the information. These are the only possibility at the state Q0, means at the state Q0, your input can be A and nothing you have stored earlier, means top can be Z0. So you are pushing, or you can have input is B and nothing at the beginning, only stack contains Z0. This means effectively stack was empty, nothing was there except the initial stack content. So you can push onto the stack. Sometimes you may find that okay, input is A, top is A. So your job, you are at the state Q0, so you have to push. You know that you are going to push onto the stack. Input is A, top can be B, you are going to push onto the stack. You can have the input is B and top is A, you are going to push B onto the stack like this. Input is B, top can also be B, so you have to do like this. One more possibility is here that your X can be null because you have taken X can be taken from the AB clean star. So X can be from the AB clean star. So this can be null also. It means you have only the single C. So whenever you have the C, once you have the C, then actually you come to know that okay, yes, I have come at the midpoint. I have at the midpoint, and now you need to match the next part of the string. You can have like this. So you are going to the state, say Q1. This is the Q1. Now see, you are at the Q0, your input is C. Once you have the C and top is Z0, this means what? When you are going to receive C and top is Z0, this means your X is null. So what you need to do? Actually, we are not going to post C onto the stack. C is just like the marker to know that okay, we have reached at the midpoint. So you don't require to change the stack content, and you are not going to push C onto the stack. This is the possibility. Or it may happen that you have some element onto the stack. Your stack can have some elements, like you have the situation. Your input can be like A, B, C, and BA. You may. So this was Z0. Whenever you have received A, and you have next is what? B. This may currently be there. Once you receive C, then you come to know that input is C. and top can be B. So what is your aim? Your aim is not to store anything onto the stack. Just you come to know that, okay, yes, I have reached at the midpoint, and you just, without changing the top, you are going to change the state. You are going to Q1. You may have other possibilities. Instead of A, you can have, for some other strings, you can have the, instead of B, you can have the A. So you are not changing the top, and you are going to transit the state. So from Q0, once you receive the, once your input is C and top contents can be either Z0, B or A, what you are going to do, you are not changing the stack top, you are going to change the step. So from Q0, you are going to transit to the Q1. Once you are at Q1, then machine knows that, okay, now I am going to read the next part. So whenever you are going to read the next part, like BA, so what you need actually, you need here only, if input is A, then what should be there? If input is A, so what should be, if it is matching, like you have the, if you have only this kind of, only A, C, A for example. So once you are, for the C you have transited, and once you are at Q1, you have the A you need to read, and what you have stored earlier? You have stored earlier A. So A will be in the top. So whenever you have, your input is A and top is A, it means your matching is done. So this top is corresponds to the first symbol. So you're reading from right to left, the top is corresponds to this, then next top to top corresponds to the second symbol. So this is the reverse actually. You are going to read the reverse from right to left. So that's why matching will be done. If you are, if it is the correct, it is in the language, then if the input is A, then top must also be A. So what we need? You need to delete. If input is B and top is also B, we need to delete because matching is done. In this way we say that yes, matching is done. So okay, like in the example, you have the, if your input is only, you have the input AB and CBA. So once you receive A, if you are at the Q0, input is A and top is Z0. So you have A Z0, means this is the A in the top. Now you have to read B. Once you have the B, input is B, top is A. So input is B, top is A. You have specified the transition. Input is B and top is A. So you have BA, means B will be in the top. Now B will be in the top, A will be in the next top to top. You have now. Whenever you are whenever you are reading now C, you have the C and in top is what? B. So you are executing this. Input is C and top is B. You are not changing the top. So this top is remains same. B is remains same. You have just transited to the state. Once you are at the Q1 and your input is what? Your input is B and top is B. So your input is B and top is B because this is the reverse. So what you need to do? You are going to delete. Replacing with null means you are going to delete. So once you replace B with null means you are going to delete. Then your input is A, next input is A and top is what? A. So this is the transition in favor of you. Input is A, top is A. You are going to replace means you need to, matching is over. So you need to delete it. You have deleted. Now what happened? There is no further input. Your input exhaust. So once your input exhaust, then you have nothing to read. So you need, once your input exhaust, you have the nothing to read, and you come to know that stack becomes empty. How would you know stack becomes empty? Once you see that the top of the stack is Z0, then effectively actually stack is empty because Z0 is the initial stack symbol. Whatever symbol you have stored onto the stack, you have everything you have deleted. So once you found that, okay, top of the stack is Z0, means effectively your stack is empty, means whatever you have pushed earlier onto the stack, matching is done correctly. So you come to know that, okay, yes, we have matched here. So if input is null and top is z0, means stack become empty. We say that we are not going to delete the stack initial content. Your machine is going to transit to the state. Here it is going to the state, say for example q2, and this q2 is actually, this is the final state of your machine. Okay, this is the final state of your machine. And now see, this is the PDA for the language XCXR. So what difference you have noticed it? You have seen that at the state q1 you have many possibilities like this. Like input is a, you may have the possibilities like input is a and top is b. You have not included this transition. Input is b, top can be a. You have not included this transition. So whenever you have not included such transition, you have not defined the transitions, means that combination you don't want at this state. And if such situations comes, then your machine is going to crash. Your machine is going to crash. And once your machine is going to crash, this means it is not in, your given input is not in the language. Like if you have A, B, C, and you can have, say you have the B and BB. If you are given this input, so once you are given this input, then whenever you are at the Q state Q0, you are going to read A, so you have to push it onto the stack A. Then you are going to read B, you have push onto the stack B, so you have read B also. Once you have the C, you are going to change the state, you are going to change to the Q1 without modifying any stop, and then at the state Q1 you are going to read B, and you see that B and top is also B, so you have deleted this top, you have deleted this top. Now your input is B, you have the input now, your input is B and top is A. So input is B, so you have the input is B and top is A, and this transition you have not specified here. This means your machine is going to crash. Once your machine is going to crash, then we say that the given string is not in the language. This is the, so the transition you don't want, the transition you don't want, you may not specify. If such combinations comes, then we believe that machine is going to crash. Similarly, at the state Q2, if you are at the Q2, okay, whenever you are at the state Q2, you may have the other situations, like you may be given the string like this: A, B, C, and B, A. This may, you may be given the input like this. So what you have done, you have read A, you have saved onto the stack, B saved onto the stack. Once you have C, transit the state, you are coming to the Q1, input is B and top is B, matching is done. Input is B, A, top is A, matching is done. Now you have input is not exhaust. Input is not exhaust. You have remaining input to be read is what? A. But what happened? You have everything, whatever you have pushed onto the stack at the state Q0, everything you have popped out, and nothing onto the stack, means stack becomes effectively empty, and the top of the stack is only containing the Z0, and but input is not exhaust. So what happened? Your machine, since it will try to find out this transition, your input is A and you have not specified here, but your input is A and top becomes Z0 here. So machine has this null transition, machine can make the null transition, and using the null transition, since top is Z0, then you will be allowed to transit the state. So machine, by taking the null transition, since top becomes Z0, everything you have popped out, so top becomes Z0, your machine is going to the state Q2. Once machine is at the state Q2, it has to read the input A. Machine tries to read the input A, but since you have not specified any transitions at the state Q2, this means machine is going to crash at the state Q2. What happened? Even you have reached to the final state, even you have gone to the final state, but machine is going to crash at the state Q2 for the input you have given A, B, C, B, A, and A. If you have given the input this, this is the reverse of this, and further input you have, if you supply this input, since this is not in the language, this is not in the language of palindrome, so what for this actually machine is going to crash for reading up to this part, reading up to this part, consuming up to this part, A, B, C, B, A. You have seen that A, B you have read at the state Q0, then you have matched B with B and A with A, and effectively your stack becomes empty but contains only Z0, and by using the null transition you are going to the state Q2. So you have reached to the state Q2, but remaining input you have to read at that state is A, and your machine is going to crash. But what input you have consumed by reaching the state Q2? You have consumed A, B, C, B, A. So actually, even you are in the final state, your machine may crash at the final state. Once machine is going to crash, this means the given string A, B, C, B, A is not in the language. But the substrings for which you have reached to the final state, what is the substrings? This is the substring for which this string caused the machine to reach to the final state, and this is in the language actually, but whole string is not in the language. So when you see that whenever you reach to the final state, and if you're once you reach to the final state, and if nothing to read next, okay, if nothing to read next, then you are going to accept the strings. Otherwise, once you reach to the final state, but you have further input to read next, and you have not specified the transition for that input, then your machine is going to crash. Or if you have reached to the final state, there is no issue. But if you have specified the transitions for some input, then for some other language you may do like this, then your machine can go to some other state. So this is the way your PDA is going to accept the information. So once you reach to the final state, the string for which you have reached to the final state, that substring is in the language. But once your machine is going to crash at the Q2 because you have further input and you have not specified the transitions, then your machine is going to crash, then whole string is not in the language. So these are the combinations you have. So what you have think, this machine is deterministic or non-deterministic. You have the null transition. You have seen the null transition here. This is, so see this is the machine you have. So you have the machine, okay. And this is your machine, and we assume we are included. Now this is the machine. Now consider this machine. Can you see this machine as the non-deterministic case? Even the null is present here. In case of the finite automaton, whenever null is there, it is 100% guarantee that your machine is non-deterministic. But in case of your PDA, even you have the null transition, then your machine may not be non-deterministic. It can be deterministic one. What is so? So here you see that. Here you see, you may think that you have the A, B, C, and B, A, for example, and you have read this, you have stored this, you have stored, okay, and now you are going to match this string with this string and this string with this. So you may think that whenever you are at the state Q1, you have the input to be read, but even the null transition is there. You are not allowed, actually, you will not be able to consume this null transition. Why it is so? Because for taking the null transition, you have to also see the top of the stack. You are able to execute this null transition if and only if the top of the stack is Z0. So when the top of the stack is Z0, then only you will be able to take the null transition. Otherwise, you are not able to take, even the null is present here, your machine cannot guess that, okay, I will not consume the input, I can transit the state. Your machine is able to transit the state if and only if the top of the stack symbol is Z0. So this this is preventing, stack contents of the top is preventing to execute the null transitions, and that's why your machine may not or may not be non-deterministic if a null transition is present in the PDA. One thing is more, every transition you have see that from every, you have the unique output, only one output. You are not having the more than one output. So you are in the state Q0 for the input A and top is Z0. You are in the state Q0 and you modify the stack top as AZ0. So you have the one. For every input from the current state, you have only one unique transition. Okay. So once this is the situation of what? This is the case of the deterministic one. So this is actually deterministic machine. This is the deterministic PDA. And deterministic PDA we denote by writing the DPDA, deterministic push-down automata. So this is the difference actually, where you see that even presence of the null transition is not sufficient for this case for machine to become a non-deterministic one. Your machine may not be non-deterministic. So when output of every transition is unique and machine is not required, simple concept is for the non-deterministic what? For the deterministic one is what? When your machine is not required to make the guess, then this is the case of deterministic one. So even you have seen that the string which is not in the state like A, B, C, B, A. So A, B, and this is reverse. Then you have the next input to be read, you are at the state Q1, and next input to be read is what? A. You have not specified the transition, but stack top becomes Z0. So you have the unique way. Machine says that, okay, yes, I have to, since you have the transition for the null and top is Z0, I'm going to take this transition and it reaches to the state Q2. And at the Q2, it is going to, you have not specified the transition, your machine is going to crash at this. So even the string is not in the language, your machine is not required to make the guess at the state Q1. Your machine will transit by observing that the top of the stack is Z0. Okay. So this is the notion of your PDA, push-down automaton. So you have the push-down automaton. Here you have the, you can make the decisions on behalf of the input, on behalf of the current state, and on behalf of the stack contents of the stack contents. So here also every CFG, which is the deterministic CFG, the language accepted by the DPDA is actually the language accepted by the push-down automaton is what? Context-free language. Context-free language. PDA is the device for accepting the context-free language. Okay. Since this is the DPDA, we will say that, okay, DPDA accept the deterministic push-down automaton is going to accept the deterministic context-free language. However, we will see later on that you will have the NDPDA also, which is the non-deterministic one. NDPDA can accept all kinds of context-free language. Okay, so here you will see that for some context-free language, it is also not possible to construct the deterministic PDA. So you will have, but you will have condition only. We know that for any context-free language, we have the push-down automaton. We have some push-down automaton. That automaton may be deterministic or may not be deterministic, but we guarantee that if the language is context-free, then we will have some PDA.